is to competitive programming. Okay, so let's start the session then. So first of all, so today's topic, time complexity and data structure. So you might think, why do we even need data structures for competitive programming? So what you have to understand is that when you, as I said before, so when you go into a competitive programming competition, um, and maybe you have already seen some sites that do those kind of competition like Hacker Rank, Code Forces. There are a lot of sites. So when you go into a competition like that, you are given a question, right? And then there is a IDE part that you have to kind of enter your code into, and you can run and evaluate and submit the code. So when writing the code, what you have to understand is that the question is not like it is actually testing our ability to use those three kind of things. So in competitive programming, any competition, what they are actually testing is whether the person has some knowledge on algorithms. So does he know how to utilize data structures, and does he have some kind of puzzle solving or problem solving ability? So all these three things are the main components, I'll say, main components of competitive programming. So if you have algorithms, if you know data structures, great, but you also need to have some kind of like creative thinking ability. So to apply those knowledge into the problem, and vice versa. If you have, but even if you have some kind of creative thinking, you also need to have some knowledge on data structures and algorithms, because like these are the tools that you can use. If you are going for the battle, you need to know of the sword and the equipment you have, right? So with the similar thing. So if you are going to the competitive programming competition, you need to know of your arsenal. You need to know of your algorithms, data structures, and so on and so forth. But the thing is, when we talk about data structures, array is a data structure, right? So variables are data structures, and one can say actually it's possible to code any kind of problem in just using one data structure. Like if you know only array, let's say you know like variables and arrays, and that's it. That's all you know. And quite actually, it is possible to solve any competitive programming problem using only using those two, right? So if you have some kind of idea of what a competitive programming competition looks like, maybe you will understand, right? In every kind of question, it is possible to use just arrays and simple data structures to solve it. But the problem is like uh, before coming to problem, so if you think of it like that, so you will have the problem. And then why do we even need other data structures? Like why can't we just master arrays, and why can't we just master using simple variables, and why can't we use just like use them and not learn about other things, right? So that's the reason. So competitive programming is not about solving the problem in any manner like possible. So if you are given a question, there are three possible like when you run the code, maybe I'll show you some kind of IDE here. Let's see. So HackerRank is one of the uh, let's say IDEs you have. So this is some kind of question you get in a competitive programming competition, right? So there is this problem. You have a huge problem, and it gives some sample input and sample output and so on and so forth. And the other side, there is the IDE for you to code. So if you run this code, so for example, if I run, I can it. if you run this code, you will actually get one of those one of three possible uh, issues. Like for if it can pass, obviously it can say correct answer, but otherwise you will get one of these three. It can say wrong answer, which means obviously the code we put is wrong, and maybe we understood the problem wrong. So because of that, the answers it gave is the program we wrote gave is wrong. So maybe we need to reread the question. Maybe we didn't understand the question correctly. So maybe there is some edge case. So if there are like 10 test cases and 8 of them pass, but 2 get wrong answer, that means maybe there are some hidden edge case that we didn't think of. So that is one possible result. And another possible issue is runtime errors, which means our code has some kind of error. Maybe we have to we have divided some number by zero or something like that. So there are some errors that we didn't handle, and because of some edge case, it's been the error has been thrown, and because of that we get an error. And the third issue we run is timeout. So timeouts means our code is actually too slow. So this timeout thing is actually the most, I'd say, most dreaded message we can get in a competitive programming competition. So basically, when we get a wrong answer, we know, okay, we need to reread the question. We need to, there is some edge case, small edge case we have to understand. Okay, we'll do that. If we get runtime errors, we understand, okay, so there's some error in our code, we have to analyze it. Uh, and o- Otherwise, there is some edge case, something like that. But if we get timeout, that means there can be many reasons. One main reason is that our approach we used, or with the data structure we used, or the algorithm we used is too slow. So when we get that timeout message, we have to understand, we have to rethink our arrays and impose our solution. uh, the problem you run into is that almost all the time we will be getting this timeout message, because that is not the approach they are expecting of us. So because there are several data structures, I'll show you some, there are many more, and each data structure is good for one specific thing. And some data structures are not good for some specific operation. So we have to understand what this data structure is good at, what this data structure is bad at. So if you understand that, then you will know when to apply them, and because of that, you will be able to use the expected data structure on the question and get the correct answer. Otherwise, you will end up running into this timeout error. So that's the main reason we need this topic at all. Like when talking about competitive programming, why we need data structures is because we have to understand some data structures are good at one thing, and we have to pick the data structure according to the requirement or the problem we have, and we should understand, okay, this data structure will be good at this task and will help my code to run this fast or something like that. But in this in the next slides, I'll be going over time complexity. And I hope you guys have some knowledge on time complexity. And I'll give you a small refresher. Then I'll be moving on to some data structures. Like I won't be talking about the primitive data structures, but I'll be talking about list, hash set, stack, queue, and then a bit on graph and trees. And in each topic, I won't be discussing the in details. Like as I mentioned before, I won't be going into the theory. I won't be going how you can, for example, I won't be going into how you can implement a stack. I won't be discussing that. What I will be discussing is how you can use the stack, how you can, what operations are possible in a stack, and when you can use them. So basically, we will not be looking at how we can implement these data structures, but rather on how we can use already implemented ones. So first, let's look at time complexity. So have you guys like heard of big O notation before? Are there people who have heard of big O notation or familiar with it? Maybe in, uh, maybe in your algorithm class or somewhere. Have you guys heard of big O notation? Okay. Yeah. So I'll be going over the like uh, like as I mentioned before, I'll be just going over the like giving a small refresher. But why we need big connotation is that like when we are discussing, let's say when we are comparing two cars, let's say we are comparing cars, so we need some kind of metric to compare them, right? So if we are comparing two cars, maybe we need to discuss their speed. So this one is faster than this one, something like that. So when we are discussing their structure, so algorithm, we need a way to we need a metric to compare them. We need to say, okay, this one is faster than the other one. So that's why we use big O notation. To be honest, big O notation is not a big part on this webinar because it's a whole another section in computer science. Uh, but as an overview, what you have to understand is that big O notation is a way we can compare two algorithms. So, intuitive idea. So, what big O notation means in like a very high level idea is that big O notation is how your operation or the algorithm scales with input size when you take the worst case. So, if you when your algorithm like when you consider your algorithm and if you consider the worst possible case, how well your algorithm will scale depending on the input size. So that's what the big O notation is. So I have a video here to explain big O notation. I guess I'll play it, but I'm not sure whether the audio will be. Can you hear the audio? Can you hear the audio or no? Okay, okay. I think you guys can't hear the audio. Then I'll skip this slide because it won't be meaningful otherwise. So, so in like what big O notation is basically how will your algorithm scale. So, for example, let's say this is your algorithm, right? And your algorithm takes some input and it gives some output. And let's say you give a input of size 10 and you say, okay, in the worst case, it will take around 10 seconds. Like what I'm giving here is like a very gross oversimplification. It's not actually what big notation means, but just an intuitive idea what that is. So you have an algorithm and you say when I give a input of size 10, for example, array of 10 elements. When you give an array of 10 elements, it takes 10 seconds to run. So you ask, okay, if I give a array of 20 elements. What is the time it will take? So let's say your answer was 20 seconds. So then you ask, okay, if I give 30 elements, what is the time? It's 30 seconds. And if you give it n elements, what is the time? So basically it will take around n seconds. So in this case, we say, okay, your algorithm has the big like worst case time complexity of big O of n. So it's something like that. So uh, more intuitively, if you think like if you want to calculate the big O time complexity of your algorithm, what you can do is basically think of it like this. So if you have some kind of statement like this, uh, some individual statement, just calculation. So you can think, okay, this is big O of 1 because no matter the input size, no matter what y and z numbers are, it will always take one like a constant time. Like even if you have 100 or 1,000 or 1 million, it doesn't matter. It will always take the same time. So we say it has a constant time or big O of 1. So let's say you have a for loop. You say for I in, I'm using Python here, but doesn't matter. So for I in x, print I. So in this one, it will run like if you have n elements in x. So for example, there are 10 elements in x, it will run, the loop will run 10 times. If you have 20 elements in x, it will run 20 times. So this for loop runs like it basically scales linearly with the input size. So if you have n elements, it will run n times. So we say this has the worst case of big O of n. So if you have, for example, two, two for two for loops. So for example, something like this for I in x and for j in x, and you I and j. So this has for two loops. So the outer loop it runs n times, and in each iteration the inner loop runs n times. So the statement alone it runs n squared times, right? So we say this has the time complexity of 4n squared. So likewise, you can build it up from here. So basically, you can think of big O notation like something like this. So if you have an algorithm, like I'll actually recommend you doing this because one might see this as like some meaningless thing. Why do we even need big O notation? But I say it's a good practice. So if you have an ability to like quickly say what the big O notation of an algorithm just from seeing it, I think it's a very valuable skill for you to have as a competitive programming competitor because then you will be able to guess, okay, this algorithm will be slow or this algorithm will be fast, right? So basically it's something like that. So you can understand this one, it is obviously faster than this one because you can see this is just a one statement. This is a for loop, but comparing from the big O notation as well, you can see this has a big O of n, this has a big O of 1. So obviously, uh, this is the order of magnitude greater than the first one. So the third one is worst. So it has n squared. Obviously, you can understand. Sorry, uh, n squared is like worse than n. So even from seeing the big O time complexity, you can understand, okay, this one would be the worst algorithm, and this would be the best algorithm, something like that. So this video, I'll share the slide set afterwards. So if you have time, go watch this video. It actually explains how you can calculate big O notation of a algorithm. Uh, but I just gave the very brief intuitive idea, not the exact, the theoretical one, but the brief one. So let's continue with the session. As I said before, some the time complexity for example, this one big of one, it is like less complex than log n, which is less complex than n. So the complexity rises with the like in the upper direction. For example, big of one is better. We say better than log n, and log n is better than n, and n is better than n log n, and the worst one is in the list. The worst one is the factorial one. So we have put some names as well. So for example, we go if the time complexity of algorithm is big of one, we say it has a constant time. It's a constant time complexity. And for log n, we say it's logarithmic, and for n, we say linear, and likewise. So why this complexity matters is with the input size. So you can think of the x-axis as the input size. With the input size, the time or the operations it has to perform increases in the as the lines here. So for example, you can see in log n and 1, those two are actually very they don't actually even like visibly increase. They are uh, they perform same for one element as well as maybe let's say 1,000 elements, because the operation that they have to perform is almost the same, because the line is, you can see, it's very flat. So those algorithms, we say they are excellent algorithms, because no matter the input size, they will take a very same kind of time, no matter the input size. So if even if you have 10 elements, 100, 1,000 or million, it will if it takes 1 second for 10 elements, it will take 1 second for million elements as well. So we say those algorithms are, if your algorithm has log n or constant bigger time complexity, then we say those are excellent algorithms. And then there is linear. Linear algorithm, you can see them, it's a straight line. Basically, with the elements, if for example, if it takes 10 seconds for 10 elements, for 20 seconds, it will take 20 elements. For 30 seconds, it will take 30 elements. So it increases proportionally. With n log n, you can see the line starts to grow in a kind of exponential manner, because here the you can see uh, we call this, even though we call this bad uh, time complexity, that's just in comparison to big O of 1 and big O of n. But basically, n log n, its time complexity increases. Like with number of elements, it gets worse and worse. And these are actually way worse. You can see, like, for example, the factorial one, even for small elements, it goes to like a very large number of operations. So likewise, you can see if like what we try in competitive programming when we optimize for time, if we have a correct answer, we have correct answer, but we get this timeout error, it probably means that maybe they are expecting uh, big O of n, but our algorithm is big O of n squared. So what we try to do is try to lower this to big O of n, and try to pass the test cases. That's what we try to do. Okay. Uh, okay. Okay. So time complexity, this is kind of a tip. So you can use, so basically every question you get in a competitive programming competition is, as I told before, it has some kind of format. They give the question. So, for example, I'll go for a if even if I go for a different question, it will have same format. So it will have a question. It will have some examples or something like that. It will have a section describing what is the input format they give and what is the output format they expect. And they will also have this section called constraints. They will have this section called, okay, these are the basically it describes in the input side. So here it says S1 and S2 are characters in the range and they have the length of between 1 and 10 to the 5. So 100,000. So basically they are saying this S1 will have the maximum length of 100,000 characters. So that's your input side. That's the N. So from that you can actually deduce what is the time complexity they are expecting. So for example, if they give a input size of less than 20, it probably means you have to uh, try, or you can actually, it doesn't matter. If the input size is less than 20, it means the approach doesn't matter. You just have to code it in. It probably has some kind of permutation, so subset kind of thing. They probably expect factorial law, the exponential time complexity, which means maybe the question is probably one the very easy question, or probably it will be a very hard question. It doesn't matter. Like if the n is less than 20, it means that they don't care. The input size is very small, so they don't care about the time complexity. Maybe because the algorithm is extra hard though, but the question is extra easy. So that's what n less than 20 means. So if you have an input size less than 500, that means what they expect is cubed, which means there are probably in your code, there is probably three nested for loops. So as I mentioned before, for n less than, if n is less than 20, it probably means you have to try all the combinations. If n is less than, let's say 500, yeah, 500, it probably means you have three for loops, nested for loops in your code. Like in the expected algorithm, there are probably three nested for loops. Probably because we can't be sure, but it's just a guess, we are guessing based on the question. It maybe it's wrong, but most of the time it's correct. So if it is less than 500, it probably means in the expected answer, they have three nested for loops. And if the n is less than 5,000, it means, so this is n squared, right? N cubed, sorry. So if n is less than 5,000, it means they have the expected time complexity of n squared. So there are probably two nested for loops. And if your n is less than 10 to the 5, so basically, even in the example, you can see 10 to the 5. So that means they expect the time complexity of n log n. So probably involving sorting. Or maybe it involves a data structure that takes n log n time. So basically, I will come to data structures and discuss about the time complexity. But but 10 to the 5 power of 5 means is probably you have to sort the input somewhere, or there is some data structure that you have to use that has log n time complexity in some operation. So that's what this means. And if your input size in 10 to the power of like less than 10 to the 7, that means it's linear. So probably there are no nested loops. There is only just one loop. If it's less than this, that means you can only be a, can use only one loop. You can't, if you used two nested loops, you will probably get timeout. And any larger than that, that means they either use something like binary search, or there is a simple, very simple equation that you can put the numbers and it will give the answer. So something like very, uh, it doesn't have to be simple, but some kind of algorithm, sorry, equation that you can get the answer out of. So that's what uh, large number of n means. So that's so I guess this is the reason why big notation is kind of important, because not only you can like compare algorithm, but you can kind of deduce from the input, like from the question alone, you can deduce, okay, this kind of solution is what they expect of. So this is the guess. Sometimes they give, for example, for equations, if even if it is a equation, they may give that n should be less than 10 to the power of 5, because uh, like equations were for even larger n, so it doesn't matter if they give a small number, but most of the time, especially in competition like IEEE Extreme or those competition, the the input size is kind of a hint towards what they expect of the approach. So yeah, moving on. So yeah, that's what um, I wanted to discuss in big connotation. So basically we learned what big connotation is. Obviously, you should have some kind of theoretical knowledge, but I won't be discussing them here. Those are like very mathematic based, and I don't want to discuss them here because they doesn't, to be honest, doesn't matter much in competitive programming domain. But it's better to have a in-depth idea on what they are. But what I discussed was basically what big connotation is and how you can use big connotation to kind of deduce the approach you have to use. And then we come to the main part, their structure. Uh, and first we'll be looking at basic data structures. So you probably already know of some data structures by now as well. Like even if you use a variable like, let's say you use a variable like x, you say x equals 10. So this is a data structure. Like if even if it doesn't seem like that, this x is a data structure. It is a simple, like in the memory, it's a simple location that holds a value. So that's what the data structure is. It holds data. But those are very simple data structures. Like we don't even talk about them when we talk about data structure. So there are other data structures, and you probably have already learned, like heard of them. I'll be going to only like few. I won't be going to everything, but I won't be going to like I'll be going to some major ones only. And yeah, so first stack and queue. So I'll explain what the stack and queue is from a drawing. So maybe you probably have heard of stacks and queues, because those are the most common entry points when we talk data structure in lectures. Those are the most common entry points we talk. So when we talk about stacks, stack is some kind of a, like, is what the name is. So a stack, a stack of plates. So when you have stack of plates, you have, you put plate one, plate two, plate three, plate four, and when you want to take a plate out, you take from the top, right? You take the topmost plate and then the next plate and the next plate, and then you put another plate. When you you put at the top, and when you remove from the top. So that's what the stack is. So in data structure terms, so what happens is there are two operations. push and pop. Push means we put a value into the stack. Pop means we remove value. So let's say we push 4. That means we put 4. Then we push, let's say 10. That means we put 10 on top of 4. If we push 12, that means we put on the top, right? So we put 12. And let's say we want to pop. When we pop a value, what happens is we take the topmost value, like uh, we take this one now. So pop will return 12. And so pop will return 12, and this 12 value will be removed. And then if we pop again, it will return this one, 10. And 10 will be removed from the stack. And if we push again, let's say we push 6, it will be pushed to the top. So basically, we put at the top, we pop from the top. So stack is the last in, first out. So basically, what we put in the stack last will be the first one to go out. So that is a stack. Queue is the other way around. So I think the queue is also what is takes in the tin. So basically, you know queue, right? So in a queue, there is a like there are people in a queue, let's say, and you join a queue from the end, right? And you leave a queue from the start. So if you join a queue early, you will be the first to go out. So that's exactly what it means in a queue in a data structure as well. Like, in a queue, there are two operations we called enqueue, basically joining a queue, and dequeue, basically like going out from a queue. So let's say we enqueue 5, basically 5 will join. Then we enqueue 6, 6 will join. We enqueue 7, 7 will join. And if we dequeue, which means this one will be the one to go out. So joining will happen from one side, the leaving will happen from other side. So if we dequeue, 5 will be the one to leave. And if we dequeue again, 6 will be the one to leave. Likewise. And if we enqueue again, let's say we enqueue 10, 10 will join at the end. So that's basically queue is. So in a queue, first one to go in will be the first one to go out. So if you join a queue early, you will be the one to leave the queue early as well. I think it is clear by now. I think this topic is kind of clear, right? So I'll be moving on to the code examples. In the slides, I have some simulation links as well. Maybe you can play around with them if you want. For example, this is the simulation of a stack. So if you want, you can try it. So basically, if you put a number and press push, you will see, okay, the number went into the queue, the stack. And if you put another number, that number will go there. And if you now put another number, that will go to next. And if you pop a number, the one at the end will be the one to pop. So you can play around with it. So I won't be like, because I explained, I won't be going to this again. But the links are there. So if you want to play around, you can. I will share the slide set with you at the end. And yeah, okay. So this is the Java code for stack. So there's this stack already in uh, uh, details library. So you can just import it. You don't have to re-implement it from the scratch. Like it's the thing I've seen in sometimes in competitive programming competitions. The mostly the new students, what they do is when they get a question, they try to implement everything by scratch. Like if they see a question and they think, okay, we have to use a stack for this, and they what they do is they end up actually creating the stack class or something like that, and they end up implementing everything from the ground up. But you don't have to do that, right? Because in almost all programming languages, there is some kind of a uh, built-in library or built-in package that provides these basic data structures. So you can just use them, right? So you don't have to re-implement everything, because time is what matters in a competitive programming competition, and you don't want to waste that time on writing the basic code. What you want to do is you have to waste that time doing problem solving and using data structures, not implementing them. So in Java, there's this stack class you can just import, and you can use it to push and pop basically. And yeah, this is the code for queue. Queue as well. There's this array DQ class, and there are other queue implementations as well. So there are this queue you can import, and you can just use it in Python as well. In Python, you can use a simple list as a stack, and if you want to use a queue, you can import it from the collections package. In the built-in collections package, they provide the queue, the queue data structure, which basically acts as a queue. Okay, so I hope these two are clear to you by now. So I'll be moving on to the next. So arrays. So arrays are like, I think almost anyone who knows at least one programming language, they know. So basically, what array is basically a data structure that allows you to access elements by its index. So in memory, what it looks like is, I mean, as a gross oversimplification, not actually what is in the memory, but you can think of it as like a continuous set of uh, uh, memory locations. So like this. So if you say, get me the value of index 0, this is the one that refers to index 0. This has index 1, this has index 2, this has index 3. So you can actually store values arbitrarily, because in a stack and a queue, what you can do is actually get either the first or last, right? But in a array, you can randomly access. So basically, you can access any value from the index. You can store values from the index. Likewise, you can access, insert, delete element by index. So basically, you can think of it like this. So in this array, it's so if you say uh, value of index 1 is 4, something like this. But arrays are very like the arrays are, as I said before, arrays are very popular. Like almost everyone knows arrays. But the problem with arrays is that they are too flexible, I say. So, like we end up using arrays in almost all the places, and there are situations that arrays are not suitable. For example, searching. So, if you have an array, let's say their input set, and you have to search some value. For example, if you have to check, is 5 in this list? You have to check that. So what you have to do is basically the basic idea is you have to loop. You have to loop over every element, checking is this number 5, is this number 5, is this number 5. Likewise, you have to check each number. So basically, checking each number, which means it has the time complexity of big of n, because you have to check in list of n elements, you have to check n times at the worst case, because like if the five number is here, you can stop. But what if there is no five in this list? You have to check each number and see it's not there. And that's the worst case, right? So in the worst case, it will take n operation. So we say it's the big of n operation. But what if you have to search n times? Like you have n elements, n elements, or let's say uh, m elements, you have to search in an array of size n. So you have an array of size n, and you have a set of m numbers. You have to check each individually whether they exist in this array or not. So you have to take one number, check it, and then take the second number and check, then third number and check. So basically, you have to have two for loops. So one for loop for each number in this one, and one for loop for each number is in the array. Basically, you end up with the time complexity of n times n. But this is not good. So n times n means if you have let's say 1,000 elements and 1,000 numbers to check, you have a million operations, right? So this million operations you have to do. So it's slow, basically. So searching arrays are not good for searching because you have to check each number. So searching in an array is a big of n. So when the list gets bigger, time to search gets lower in the same order. So when you have a big array, you have to search and searching gets slower. And you have to search continuously, it gets even slower. So uh, if you have searching, you have to perform searching. That probably means you should not use the array. But there are some caveats, right? Like everything in life, there are some caveats. So one major caveat is like one major thing that you have to think is, yeah, you have to have a sorted array. Sorry, you have to have a sorted array. Sorry, you have like sorry. So if you have a array, searching is bad. But if you have a sorted array, let's say this is array, but it is sorted one. So basically, the elements in it are sorted. Maybe uh, they are in the increasing order. So you have a sorted array. This is not a sorted array. So if you have a sorted array, then there is this algorithm called binary search. So as I said before, this takes big of n time to search one number for one number. So if you have a sorted array, you can use binary search algorithm, which is a different algorithm, which reduces this to log n. So if you have a sorted array, you can use this binary search to make the searching faster. So if you go back to the time complexity chart, you will see, so big of n is this one. It's the fair algorithm, and log n is in here. It's the like excellent one. So you can see the difference. And as I said before, if you have to search m numbers, or let's say we have to search n numbers now, so then the time complexity becomes n squared. But this one, the time complexity becomes on log n because we have to do this 10 times. So this one means, so from this one, we can go up to input size of 10 power to the power of 5. But with this one, we can only go into inputs like 5,000, as I mentioned in these slides. See, so even if you use arrays, there is a way to use it in so you can first sort it, perform one search again and again and again. That would be faster. Like if you have to, for example, let's say you have to you have an array, you have a number of elements, and you have to search for some numbers as I said before. And one approach is just search each number. And the second approach is sort first, then search each number, but use binary search. So you might think, okay, the second one we have to sort as well, like it's probably slower, but as I mentioned before, like as I explained, this one has the n square time complexity, while this one has n log n. So this one is better. So likewise, you have to understand, like even if I mentioned arrays are bad, there are some situations you can still use them for searching, right? So search. But then I'll move on to the hash data structure, which are like more suited for searching. So you will see. So in hash set, so up to now we talked about arrays, stacks, and queues, which are basically heaping elements regardless of their value. But hash sets, they keep only unique values. So you can't have two fives here. If there is 1, 5, 3, 10, 2, 9, you can't have two fives or two threes. Like there can only be unique values. But that is actually, that might not be a good thing. And they don't have any particular order. You can't say there is no indexing. So you can't say give me the zeroth item. So it is in one. You can't. There is no perception like the you can't index anything. So, but this might seem like a bad thing, but the thing is, there are some operations that these things are very good at. So, for example, insertion, deletion, and searching, they are all, we say, big of one. Basically, uh, the best you can get. So, insertion, deletion, and searching is big of one. So, they are very good. Like they are excellent as a general purpose data structure, but you can only store unique items, and there will be no preserved order. You can have a order, but time complexity will be like very fast. So, so, so hash map. So this is the hash set, basically having a set of numbers, just that. Hash map is a kind of extension for that. So basically, they store uh, the number as the key, and they can have some value as well. For example, uh, they have key value pairs. They don't have a order like I mentioned before. Uh, Similar to hash set, they don't have a order, and they can only have unique keys, but they have insertion deletion of big O of one and searching is big O of one. So there are few caveats. So keys should be hashable and they have big of one time complexity. And as the catch, the only catch is they have unique. They have to be unique items and there is no preserved order. So yeah, I show a small. Sorry, this is the hash map, right? So uh, the link is there for the simulation. I'll actually draw and show. I think it will be better. So in hashing, I won't be going into hashing or anything like that. Just the idea is that you can have like if you there is this big bucket of numbers, right? You can put numbers in, you can get numbers out, This is big of n, and you can search, and that is also big of n, big of 1. So, for example, like in the previous one, we told two ways to use an array. So, searching n times in the array of n elements. We said one approach, we go of n square. The other approach, n log n. But if there's a possibility we can use a set, then it will be actually big of n because it doesn't take time for searching. It's basically constant time. So it will take big of n, which is the best we can get. So if you use a set, it will be much faster. Uh, yeah. So in a set, what happens is you can put numbers in. For example, if you add one, you can add one, and if you add two, it will be put two, and if you add two again, it won't add another two because there's already two there, so nothing happens. If you add three, three will appear, and if you add one again, nothing will happen because one is already there. If you remove two, two will be removed, and you can search basically. Search for let's say tree, then it will say there, yes, there is tree there. So all these operations, they are big of one. So so in Java, you can use hash set for using a set, and for maps you can use this hash map class. These are very common as well. Like with arrays, you learn this. Most probably you have heard about this hash map thing. But these are like remember like when searching, if you have to use some kind of searching, think whether you can use a set because like there are situations you can't obviously, but if you can use a set, it will be a very big advantage on searching. But if obviously if you have to have order, then you can't use a set. So there is this, you have to know this thing is good at this and this thing is bad at this. Likewise to know what to use. And in this is how you can do use it in Python. Uh, Okay, so this is a problem. I have put the link. If you can, it will be better if you can try it out yourself in some time. Uh, maybe let's see if we have let's see. So there's this problem. If we go to the link, yeah, we go. I think I have to log in for the to answer. So maybe not today. But yeah, if you can. Go to this link and try this out. You will see that if you use a array to solve this, you will get a timeout error. But if you use a set to solve this, you will be able to solve it. So this is a very simple question that you will see that you have to use certain data structures in certain times because some data structures they are just not good at some operation. And then we come to the last part of our session. So basically, some more data structures. So here I'll just be going to very brief overview. I will not be explaining the operations or anything. I'll just go to these structures, read them if you have time and if you plan to go into a computer programming competition. I'll just be going to these things to just to inform you that this thing exists, right? Because sometimes that knowledge also is important. Just knowing that there is some kind of thing, that knowledge becomes important when you face certain problems. So, graphs. So graphs we use, these are very common. Like if you, for example, are going to IEEE stream, you will see problems that involve graphs like in, let's say there are 24 questions, you will see in at least 10 you have to use graphs. It can vary, of course, but graphs are very common. What a graph is basically a set of nodes connected by edges. So if I draw a sketch, there are a set of nodes. For example, let's say A, B, C, D. These are nodes, and then there are edges. Edges means these lines. And sometimes these lines have weights, sometimes they don't. And sometimes these lines have a direction as well to denote, okay, this is the direction. So basically what this means is there is, you can think of it like a road map. So these are cities, these are roads. So there is a road from B to D with weight of 4, basically meaning maybe there is 4 kilometers between those two cities. And from A to B there is a 4 kilometer path. From C to A there is a 3 kilometer path. So likewise, this can be used to represent road networks, flow networks as well. So, for example, how you can use it to denote flow networks is you can say, okay, there is this, let's say, town A, there's this town B, and there's this town C, and there's this town D, right? And these are kind of the pipes between a city, and these are weights. Weights meaning this is the size of the pipe. So there can be 3 liters per hour in this pipe, or there can be uh, per second, and 3 liters per second. So maybe to denote how much flow can happen in each pipe or something like that. So likewise, you can denote the flow networks and sometimes dependencies. Like there are like so many use cases you can use to denote this. For example, you can even denote friend network. So this is John, this is Joe, this is, let's say, Jane or something like that. So we can use graphs to denote friends. So basically saying John is a friend of Jane, John is a friend of Joe, Jane is a friend of Ben, but Joe and Ben they don't know each other. So something like this. So you can use graph in the various different situations, and because of that reason, they are very common in competitions as well. The basic idea is there are nodes, and then there are edges between the nodes, and these nodes can have a weight and maybe a direction, and we can use them to, like, we can traverse these graphs to solve different problems. So another data structure I'll be like briefly going through is trees. So trees is also a graph. They are also a graph, but the difference being there are no cycles. So for example, you can think of a cycle is something like this. So if you have 3 nodes, 4 nodes, let's say, if you have something like this, so if you can start from A, go to B, go to C, then and go to A again, that means there is a cycle. In trees, there are no cycles. So basically, there's a structure that looks like this. There are no cycles, and there are a whole range of algorithms uh, which relate to trees. Like there are a whole range of algorithms and whole range of other data structures. For example, there are things called red black trees, B trees, ABL trees, which are actually uh, different data structures. And one major thing is like if the tree is balanced, that means you can see this tree is not balanced. So this side is heavier than this side, right? So if the tree is somehow balanced, each operation takes log n time. So this property is very important and because you can use it to perform some operation in faster manner. But I won't be going through them or going through those operations or how you can use them here. But just know that trees are also some variant of graphs, and they are connected and no cycles. Basically, that. And some variant of graphs, and you can utilize them to solve a different range of problems. And these are also very common. And another variation of trees, heaps. Heaps are used to basically you can use them to as priority queues. So basically, let's say you have I won't be going to how to use them, but just on a very brief idea. So let's say you have a certain set of numbers. You want to take the highest number out always. Like for example, you have to you need to ask what is the largest number? 100. Okay. What is the next largest number? 12. You can do this by having sorted array, but the problem is you want to have the ability to uh, insert elements as you go on as well. For example, you want to ask what is the highest number, and you also want to insert elements and remove elements at will as well. So in these kind of operations, heaps are very useful. So these are actually used for priority queues. So basically, these in very brief manner, these are their structures, these are trees that hold the largest or smallest values in the root or the topmost place. In this is the Python code. So in Python, you can use a heap queue package to basically use a heap. So up to here, I think we have discussed very basic ones like stacks, queues, arrays, and hash maps, hash sets, and I think graphs, trees, and heaps. Before you go into a computer programming competition, you should at least know uh, these are the prerequisite. But there are a lot of other structures as well that you should know. And for that, I'll be like, these are some books I recommend. So we are coming to the end of the session now. So these are some books I recommend. So this book, especially Competitive Programmers Handbook. So I highly recommend you. So it is the open source book. You can go into this link and download it freely. And it's a book I highly recommend. So if you can like go through this book before a competitive programming competition, and maybe even during, because you can like most of the competitive programming competitions are open book, right? So you can browse internet or read books freely. So if you have this like this book has the like a handbook basically to reference, then you will be actually gaining a lot of advantage of others. So for example, it has the section on time complexity, sorting, data structures, searching, and various different algorithms, greedy, dynamic programming, and the graph algorithm, tree traversal, graph traversal, shortest path, tree algorithm, fan and trees. Uh, sh- like there are a lot of algorithm flows, and there are a lot of uh, algorithms in this book and lot of applications and how you can use these. For example, if you go into one topic, you will see what it is and how the algorithm works and how you can implement it. So this is a very valuable book. I say try to like not entirely read it, but at least go to the chapters and see what are the topics out there. So this is a very good book on that regard. And this book, Introduction to Algorithms, this is a very good book if you want to like know the theory behind everything. Like I think this is kind of like a very very famous book as well, like a book that. that is recommended a lot of time when you want to learn algorithm. This is a very big one, the huge book, and it contains a lot of theory and math, those things. So it might not be the cup of tea of everyone, but it is the very book as well if you want to learn more of algorithms and how they internally work. And I put some two sides to practice. There are lot more others. Code Forces is the one I highly recommend because there are competitions ongoing. For example, if you go to the Code Forces website, uh, so they have competitions. Like for example, even now it is a contest is running. So there is 2 hours left. You can actually see even the problems as well. So there are people are competing even now. Of course, it is a very good site because there are a lot of contests running every now and then, and it's very active as well. So even you can see the for the first problem there are like 16,000 submissions. So it's a very active site. A lot of people practicing this site, and they also publish tutorials as well. For example, you can see they publish tutorials as well to learn. So if you want to learn computer programming, this is the place. This the I say the best resource you can have. And HackerRank, it is a very standard one. You will have different uh, problems. There are a lot of others as well, Code Chef, HackerRank, and Code. Like there are a lot of similar sites. You can practice algorithms in them. But I'd say this book and Code Forces, these two are actually very good, and I uh, hope you will like gain some knowledge using them. And yeah, so that's it for the session, and thank you. And this is for the like the end of the data structure session. And if you have any questions, I'll be happy to answer. Yeah.